let us now try to convert the, let us try to examine the kinematics of fluid motion and see what kind of strain rates are happening as a fluid flows from T0 to T0 plus delta T, and as exemplified by the relative motion of the points A, B, C, D, which represent 4 fluid particles, which in an interval of time of delta T have moved to A prime, B prime, C prime, D prime. And we had said that this change of relative position from A, B, C, D to a general quadrilateral is a result of rotational strain, shear strain and extensional strain. We will quantify these things and see how we can express in terms of velocity gradients and so on. Let us consider rotational strain. What we mean by rotational strain is that the diagonal of this quadrilateral initially is theta with respect to the horizontal. Now it has become theta prime, and one can say that rotational strain is theta prime minus theta is an indication of the rotational strain. So now what is theta prime? We can say that if the bottom side has moved with respect to the horizontal through rotated through an angle delta alpha, and if the side AD has rotated in the clockwise direction by an element beta, delta beta. Now we always measure the angles in the counterclockwise direction. So this delta beta, which is actually in the clockwise direction, this is in the clockwise direction, so we should be putting it as minus delta beta. We can say that if there is a shift of, if delta alpha is positive in this direction, then theta prime would have gone in the counterclockwise direction, and if delta beta, positive delta beta, that is if this side were to come like this, that would also contribute to theta prime. So we can say that theta prime minus theta is equal to half of delta alpha plus delta beta. That is the shifting of the diagonal coming from the rotation of this side AD and the side AB. And we note that initially delta alpha is 0 and delta beta is 0. So any change from 0 value of delta alpha to the new value has arisen because of the relative moment. So we can say that rotational strain is theta prime minus theta. It is given by this. Here we measure these things, both the angles, in counterclockwise sense. We understand from this thing, when theta delta beta is negative, like this one, we have identified this as negative, the fact that side AD has rotated in this direction would reduce the rotational strain. In fact, it would make theta prime less than what it is because of the rotation in this direction. So although we have put it as delta beta, in this thing it is reduced because we have got minus delta beta. So we can say that in general, when delta alpha and delta beta are measured in the counterclockwise sense, then the rotational strain is given by theta prime minus theta, which is half of delta alpha plus delta beta. Now what is delta alpha? So let us magnify this a bit here. This is originally, this is AB, and now this is A prime B prime. So we have brought A prime and A to be the same thing because we are only looking at rotation, and this is our delta alpha. So if we draw a perpendicular here and call this as B double prime, then delta alpha is roughly equal to B prime B double prime divided by A B double prime. Okay. So that is this distance divided by this distance, that is AB prime, is given roughly by this. Now B prime, this B prime B double prime is this distance here, this distance, and one can say that this height is equal to VA times delta t, where VA is the vertical velocity of point A, vertical velocity component, and this distance here is VB times delta t. Okay, so because particle B has a vertical velocity component VB which is greater than the vertical velocity component of point A, this has gone a higher vertical distance. That is why this B prime is relatively at a higher position compared to A prime. Okay, so the difference between VB and VA has actually led to a relative movement of B prime in this. So we can write this one as VB minus VA times delta t by AB prime, AB double prime. And what is AB double prime? AB double prime is nothing but the original distance that was there between these two, okay, which is AB we have, let us say that this is point B. Okay, so this is the original distance, this much, plus this B double prime. Okay, and what is B double prime? It is the distance that this has B has traveled in the horizontal direction relative to A. So we can write this as, we can write delta alpha as VB minus VA times delta t divided by AB plus UB minus UA times delta t. Okay. So now we can write this thing as dou V by dou x times delta x delta t this is the gradient of velocity, vertical velocity in the x direction. So that is times delta x will give us VB minus VA times delta t, and this is AB plus du by dx times delta x delta t. Okay. So and this is itself is delta x, AB is original delta x, and we can write this roughly as dou V by dou x times delta x delta t divided by delta x, neglecting this thing in comparison with this, because both are delta x's and this is a small time delta t, which cancels out here, and finally we get delta alpha to be equal to dou V by dou x times delta t. Okay. So we can say that, and similarly if you consider delta beta, if you want to get an expression for this, we are looking at AD, which is the original side, and relative to this is our D prime and this is A prime. So we can say that this is our delta beta minus delta beta. We draw a perpendicular to this, which is we call as d double prime, and this is our d here, and we can write delta beta equal to d prime d double prime by ad plus d double prime, the same way as what we have written here. And this distance is because A and D have different horizontal velocities. Okay. So, because of the difference in horizontal velocity, A has moved to A prime and D has moved to D prime, and if they have the same velocity, then D prime would also be at the same in the same x velocity x position as D. But because of the horizontal velocities being different, there is now a gap between the two. So, we can write this as ud minus ua times delta t divided by delta y plus, and this d prime is again related to vd minus va times delta y times delta t. Okay, so we can write using the same argument as du by dy times delta y delta t, du by dy because particles d and a are separated by vertical distance, so their variation is with respect to y here. So, we can say that dou u by dou y at a times delta y times delta t is this divided by delta y plus dou v by dou y times delta y delta t. Again we neglect this as small compared to this, so we can write this roughly as dou u by dou y times delta y delta t divided by dou y delta y. So, this cancels out and we get dou u by dou y times delta t, and this is for minus delta b. Okay. So, now we can say that the rotational strain which is theta prime minus theta, which is equal to half of delta alpha plus delta beta here, okay, is now becoming half of dv by dx minus du by dy times delta t. Okay. So, the rate of rotational strain is this much strain has happened in a time of delta t. So, if we divide by delta t we get this. So, this is 1 by delta t of theta prime minus theta. So, that is equal to half of dv by dx minus du by dy. So, the rate of rotation strain is expressible in terms of velocity gradients of a certain combination. Okay. Now, let us consider the shear strain. We have said that this is equal to half of delta alpha minus delta beta, okay, because delta beta is supposed to be going in the counterclockwise direction and minus delta beta is coming in this direction. So, this is we already have evaluated this each term here, and this is equal to half of dv by dx plus du by dy times delta t. Therefore, rate of shear strain is half of dou v by dou x plus dou u by dou y. Again we see a shear strain rate being expressed in terms of dou v by dou x and dou u by dou y, and this is the term that we recognize as the strain rate term which appears in the Newton's law of viscosity, where tau is equal to mu times du by dy. We see that du by dy term coming here. So that is coming in the shear strain rate and also in the rotational strain rate in this way, in this particular way. Okay. Now we have the last one is the extensional strain. Let us see if we can do it here. This we said is the change in length divided by the total length. So this is a prime b prime minus ab divided by ab. Okay. And we should be specifically considering this a prime b double prime, which is the horizontal distance. So this particular thing is we have already evaluated as this a b double prime here is ab plus bb prime and bb double prime, and bb double prime was what we said as ub minus ua times delta t. So this particular thing is ab plus ub minus ua times delta t minus ab by ab. Okay, so this and this cancels out, and this ab is nothing but delta x. So we can write this as dou u by dou x at a times delta x times delta t divided by delta x. So this gives us dou u by dou x times delta t. So the rate of extensional strain is this divided by delta t. So that is dou u by dou x. So this is the rate of extensional strain in the x direction. And similarly we can show that the rate of extensional strain in the y direction and in y direction this will be given by dou v by dou y. So from this point of view, from this what we can see is that the different strain rates, the rate of extensional strain, the rate of rotational strain and the rate of shear strain are all expressible in terms of the velocity gradients which are of different kinds. In this particular case dou u by dou x, dou v by dou y here, and this dou v by dou x minus dou u by dou y. Okay, these are in the same direction like the normal strains, and these are shear strains, these are shear gradients, and this is minus here and plus here. So in that sense the various combinations of velocity gradients describe the rates of strain that a fluid particle will be suffering as it is going through the flow. And our idea is to follow the analogy of solid mechanics, in which we relate the stress to the strain in a linear way. We want to express a linear relation between stress and the strain rate. So we would like to say that tau ij is proportional to epsilon kl, where this epsilon kl, this stress is we know is a tensor, and we make up a strain rate tensor, deformation rate tensor, which is nothing but dou uk by dou xl. So the particular component of the strain rate tensor with index kl is given by uk component of the velocity and xl component of the direction. So if you were to write this out, then this will be three components there, and then three more. These are all the different velocity gradients, okay, and different components of shear and strain and shear, rotation and extension are different combinations of these velocity gradients. So we put everything here together and we make a linear relation between the shear stress, the viscous stress and the strain rate as a general expression. So we would like to capture what we are saying is that the strain that the fluid element is suffering over a particular time delta t, okay, can be attributed to some stresses acting on this phase such that the resultant will be a distortion of this in this particular way. And because these are all because of various components of the deformation like shear or rotation and extension are linear combinations of these velocity gradients, we can seek a general relation between stress and a strain rate tensor which is defined like this. So we would like to say that a generalization of the Newton's law of viscosity where shear stress is proportional to the velocity gradient can now be expressed in a general framework as a stress component is proportional to the velocity gradient component in this particular way. Now what will be the proportionality constant? If we are looking at a single component tau yx, then if you were to say that this is proportional to a single component like dou u by dou y, then you can say that this is equal to mu du by dy. This is the case where you have a single non-zero shear stress and a single non-zero velocity gradient. But in the general case we do not have a single non-zero shear stress and we do not have only one of these being non-zero. So in the general case all these can be non-zero, and if you are expressing a general relation, one particular component of the shear stress may be expressed as a linear combination of all of them. For example, if you want to put a linearity relation between the two, we should be able to say that for example tau, I will just put as xx, one component is equal to some constant a1 times dou u by dou x plus a2 times dou u by dou y plus a3 times dou u by dou z plus a4 times dou v by dou x plus a5 times dou v by dou y plus a6 times dou v by dou z plus a7 times dou w by dou x plus a8 times dou w by dou y plus a9 times dou w by dou z. This I would say is a general expression for this component being linearly proportional to all possible combinations of the strain rate stress tensor components, okay. And we should be similarly writing tau xy is equal to b1 times dou u by dou x plus b2 times dou u by dou y so on plus B9 times dou w by dou z, and so on like this for all the 9 components of the stress tensor. So if you want to express a relation, a general relation between tau ij as being proportional to epsilon kl, then we have to express this as tau ij equal to some a ij kl times epsilon kl, where this is a matrix with 81 constants, and we can see where the 81 constants are coming. For example, the first element of this has 9 constants a1 to a9, and the second element has b1 to b9, that is 9 more components. So a generalized expression between shear stress and the strain rate here will involve 81 constants, not a single constant mu. Okay, so this is a requirement in case we want to make it the most general the general relation. And how do we get these 81 constants? These are properties of the fluid, just as in the simplest case mu is a property of the fluid, this is a property of the fluids, and we have to determine all these 81 constants empirically. Only then we can claim that we have a relation like this. That is difficult, and it is also not necessary. It can be reduced to much simpler level by noting certain properties of the stress tensor and the strain rate tensor. For example, we have, although 9 components of this stress tensor, we know that the stress tensor is symmetric. If you apply the principle of angular momentum conservation, then we can show that the stress tensor is symmetric, and therefore instead of having 9 independent components in this, we will have only 6 components. So this tau xy is actually also equal to tau yx. So instead of having 9 equations like this, we will have only 6 equations. So that reduces the number of equations here. Instead of 81 constants, we should be having fewer number of constants. And the other thing is that while stress tensor is symmetric, the strain rate tensor here is not necessarily symmetric. Okay, but we can make certain assumptions. We can make the assumption that under hydrostatic condition, that is when there is no relative motion, okay, when there is no relative motion, then the stress part is equal to 0. See, if you were to, there is no viscous stress, so that means that we can break up the stress that we have been using in this into 2 components. One is minus P, that is the pressure, the hydrostatic pressure, times delta, which is the Kronecker delta, plus this tau, and this tau is the viscous tensor, which is equal to 0 when there is no relative motion. So under pure hydrostatic conditions, the stress tensor that is appearing, the sigma, consists only of the 3 normal stresses, normal compressive stresses in the 3 directions, and that this is equal to 0. And we also make the second assumption that under pure rotation, the stress is equal to 0. Okay. So that means that when we have only rotational strain, then there is no stress coming out of that. Okay. So even though the velocity gradients are non-zero in this particular case, okay, the strain rate, there is no stress coming from that. And what this implies is that relations, linear relations among these things with a negative sign here are not allowed. You can write epsilon ij, epsilon kl as dou uk by dou xl, and we can also write this as half of dou uk by dou xl minus dou ul by dou xk plus half of dou uk by dou xl plus dou ul by dou xk. If we do it, what we are writing here is that this is the typical rotational strain rate part, and this is the shear rate, shear strain rate part. Now, if we say that pure rotational strain rate does not come into picture, it does not cause any stress, then this particular combination is will not come into picture, and you have only a combination like this comes into picture, and this is symmetric. So that means that if you interchange L with K, you get the same thing, whereas here because of the minus sign you don't get this becomes, this is antisymmetric, this is the symmetric component. So we can say that only the symmetric component of the strain rate tensor will come into the linear relation between stress and strain rate, and this allows us to say that just as the shear stress component is symmetric, therefore you have 6 variables in this. Even the epsilon KL component, okay, which is defined now in this way, will also have 6 strain rate components in this, so that the relation between shear stress as being proportional to the strain rate will involve only 6 components and 6 components here, so that it will have only 36 constants. Okay, by making the assumption that rotational strain, pure rotational strain does not cause any shear stress, we can make the whole relation between shear stress and shear rate being among symmetric tensors, so that you have only 36 constants. Okay, but even 36 constants is quite tedious to find, and it is very difficult to find experimentally, and this we would like to reduce it to much smaller level, and we make the third observation. So the first observation is that no relative motion, no shear stress. The second is pure rotation, pure rotational strain, no tau, and the third is that a linear relation between tau and epsilon, and which when is between two symmetric tensors will mean that okay, now this is in general coordinate frame of I and j. Okay, so any tensor can be converted into a principal coordinate frame okay, in which out of the three out of only tau xx, tau yy and tau zz, okay, in the new coordinate frame x bar, y bar, z bar, are non-zero, and tau x bar y bar equal to tau y bar z bar equal to tau z bar x bar are 0. So, this is the principal stress directions. Okay. Instead of having x y z, we can do a transformation, for example using the eigenvalues, and into a new coordinate frame x bar y bar z bar, in which all the off normal stresses, the shear stresses will be 0. Okay. So, and only normal stresses are non-zero. So, in such a case, the instead of having 6 stresses here, we will have only 3 stresses. Okay. So, only 3 non-zero stresses, and so from tau xy, if we go to tau x bar y bar, this has 6 components and this has 3 components. And similarly, the strain rate tensor here, this is in the form of general x y z, and even that can be converted into the principal strains, and that will also have only 3 components, epsilon k bar L bar, that. Okay. So, a general relation that we are seeking now is not in terms of among 6 variables and 6 variables here, it is in terms of 3 variables here and 3 non-zero variables here. So, underlying this is the requirement that the relation between the shear stress and strain rate that we are seeking here is invariant to coordinate frame rotation. Okay. So, if you rotate from x y z to x bar y bar z bar, then you can get into the principal coordinate frame here, and also for the shear rate, and this rotation would not affect the constants that are involved in the linear relation. Okay. So, that kind of mathematical invariance means that the relation between stress and strain rate involving 36 constants should actually have only 3 times 3 9 constants. Okay. So, now if we seek the same relation in terms of tau I bar j bar as being proportional to k bar L bar, then this has 3 components and this has 3 components. So, that is 9 constants must be there. Okay. So, only 9 independent constants exist if we want the principle that the relation, the linear relation is invariant to coordinate transformation, which is usually a requirement for any good constitutive relation. So, these 9 constants, for example, can be, if you were looking at tau xx, okay, is expressed in terms of a1 epsilon 11 plus epsilon a2 epsilon 22, let me put it also as 11. Okay. We should also realize that if we are seeking a linear relation between these stress tensors, then it is necessary that the rotation that we give to the stress tensor, that is the principal axis for the stress tensor and the strain rate tensor, must coincide. So, the 1 2 3 directions of the ijk, okay, if we say that these are the 1 2 3 directions, these are the 3 principal directions, they must be the same for the stress as well as the strain rate tensor. So, we can say that tau 11 is now is a linear function of these 3 non-zero strain rates. Okay. So, and the general expression will be that this is proportional to with a proportionally constant of a1 and a2 and a3, and similarly tau 22 is b1 epsilon 11 plus b2 epsilon 22 plus b3 epsilon 33, and tau 33 is C1 epsilon 11 plus C2 epsilon 22 plus C3 epsilon 33. Here we have 3 principal stresses being proportional to the 3 principal strain rates involving 9 constants, 3 for A, 3 for B, 3 for C. Okay, so this is what we mean by a coordinate transformation involving 2 symmetric tensors, okay, being mathematically invariant, in which there are only 9 independent constants that are permissible. Now at this point we introduce the fourth condition, that we have the fluid is isotropic. Okay, when we say an isotropic fluid, then it is a fluid which gives the same stress versus strain relation or strain rate relation, no matter in which direction that is, that relation is the same in all directions. We can take an example of a paper to illustrate this. Let us take an extreme view. This is a paper and I tear it along. Okay, so if I tear it, then I am applying a shear stress because of which it is tearing, and there is a corresponding deformation, and you can see that it is tearing like this. If the paper is truly isotropic, I should get the same sort of tearing ability in this direction also, and I can see that here it is coming out very neatly, whereas here it is not coming out like that. Okay. See, it is coming out in a different direction. So this is an example of an anisotropic material in which a stress produces different strain depending on in which direction it is applied. If you have a coarse grained newspaper, like maybe a cheap newspaper, then if it is rolled in a certain way, then that changes the structure of the material, and in such a case it is normally easier to tear it along the grain boundaries rather than across the grain boundaries. Okay. So if your material that you are talking about is constituted in such a way that it has some intrinsic fault lines, okay, intrinsic strength patterns and intrinsic orientation of chains and all that, in such a case you can expect forces applied in certain directions to produce certain strains, and applied in a different direction to produce different amount of strains. So such a material is not isotropic material. But if it is a truly isotropic material, like a fine grained paper, maybe high quality paper, if you try to tear it, it tears uniformly in all directions. Okay. And this one, which may be a cheap quality paper, may not tear in the same way in all directions. Okay. So we are talking about the fluid being isotropic, so that it exhibits the same relation for strain versus strain rate versus stress. And if you have a fluid which is, for example, a polymeric fluid with long chain molecules which are oriented in a particular direction, then in such a case you can expect, because of the orientation of chains of the polymeric molecules, you could get a different strain versus stress relation in different directions. So in such a case, such a fluid containing long chain polymeric molecules may be an anisotropic, it may not be isotropic. But typical fluids like air and water, which are not polymeric and which contain fairly simple molecules like that, without any preferred orientation, exhibit the condition of isotropy. So under isotropic conditions, if you were to change the orientation of the stress, and then if you were to look at the resulting strain rate along the 3 principal axis directions, then you would find that that would be invariant. So under those conditions, for example, if you were to substitute between these two, okay, instead of 1 we make it 3 and instead of 3 we make it 1. Okay. So if you do that here, then this relation will give us tau 1 1. We are making 3 to 1 and 1 to 3 is C1 times epsilon 3 3 plus C2 times epsilon 2 2. This 1 1 has become 3 3 plus C3 times epsilon 1 1. Okay. So now if you were to compare this relation with this relation, because this is a stress applied in this, so now you can see that 3 3 is coming here, and for these two to be the same, C1 must be equal to A3 and C3 here must be equal to A1. Okay. So this means that C1 is equal to A3 and C3 is equal to A1 and C2 is equal to A2. Now let us do the shift between 2 and 3, 2 to 3 and 3 to 2 in this equation. So this will give us tau 3 3 equal to B1 epsilon 1 1, 1 is unchanged, plus B2 epsilon 3 3 plus B3 epsilon 2 2. Now you compare this tau 3 3 with what you are getting here. This means that C1 must be equal to B1 and B2 is equal to C3 and B3 is equal to C2. Now let us do in this change between 1 to 2 and 2 to 1. So this will give us tau 2 2 is equal to A1 epsilon 2 2 plus A2 epsilon 1 1 plus A3 epsilon 3 3. If you compare this with this, we get A1 equal to B2 and A2 equal to B1 and finally A3 equal to B3. Okay, now if we compare this, C1 is equal to A3, so we can just summarize this, and A3 is already equal to B3 here, and C1 is already equal to B1 here, and B1 is equal to A2 and B3 equal to C2. So let us call this as some lambda 1, okay, and we have C1, A3 and okay, let us see, let us look at C2. Okay. Now let us see where is C3. C3 is equal to A1, is not appearing here, and A1 is equal to B2, B2 is equal to C3 and C3 equal to A1. Okay. So this is it. So we have lambda 2. Okay. So out of these 9 coefficients here, 6 of them are all equal and you call that a lambda 1, and the other 3 are all equal again with respect, and you can call this as lambda 2. So that means that once you apply the condition of isotropy, the 9 independent constants become only 2 independent constants. So if you want to have a relation between principal stresses and principal strain rates which is linear and which exhibits the condition of isotropy, which is the property of the fluid, then instead of having 9 constants we can have only 2 independent constants. Using this, for example, you can have tau 11 equal to lambda 1 times epsilon 11 plus lambda 2 times epsilon 11 plus epsilon 22 plus epsilon 33. Tau 22 is equal to lambda 1 times epsilon 22 plus lambda 2 times epsilon 11 plus epsilon 22 plus epsilon 33, and tau 33 is equal to lambda 1 times epsilon 33 plus lambda 2 times epsilon 11 plus epsilon 22 plus epsilon 33. Okay, so this expression, these relations here embed a linear relation between stress and a strain rate, in which we are not forcing all the stress components to be the same, okay, and a linear relation which involves only 2 constants lambda 1 and lambda 2. Okay. So, in that sense this is a reformulation of this in the form of 2 independent constants lambda 1 and lambda 2, which obeys the condition of isotropy. Okay. So, this is obeys the condition of isotropy, and invariance to coordinate transformation, as well as symmetry of the strain rate, okay, in the sense that it only allows this kind of relation and not this kind of relation, which is antisymmetric part, in which the antisymmetric part does not come into picture. So that this is the kind of relation between which is generic, okay, which involves all the 3 dimensional dimensional strain rates and 3 dimensional stresses, and this can be expressed in the general coordinates as tau ij is equal to half of du I by dxj plus duj by dxi plus times lambda 1 mu times this plus lambda times dou uk by dou xk okay. So, this is a general relation for the shear stress and the strain rates involving 2 constants, mu, which is our familiar dynamic viscosity, which we call as dynamic viscosity, and lambda, which is called the second coefficient of viscosity. And you can see that this is a term with repeated index. So, this is the sum of all the 3 normal strain rates, which is the same as what we have here, and this is a Kronecker delta. So, this relation is a general 3 dimensional relation between linear relation between stress and the strain rates involving 2 independent constants, which obeys the condition of isotropy and mathematical invariance to coordinate transformation. Okay. So, using this, for example, we can now write tau xx as mu times I is now x and j is also x. So, this will be dou u by dou x plus dou u by dou x plus lambda times dou u by dou x plus dou v by dou y plus dou w by dou z times delta. When I and j are the same, then this is equal to 1. So, it gives us like this, and tau yx is mu times. So, I is equal to y and j is equal to x, or we can say I is equal to 2 and j equal to 1. So, this will be okay, dou v by dou x plus dou u by dou y plus lambda times this whole thing times delta yx is 0. So, this comes out as only this thing. So, this term will not be there. So, we can, using this expression, we can write down the individual components in terms of the velocity gradients and in terms of two coefficients u and mu and lambda. Okay, so, this gives us the additional relations that we are seeking, the constitutive relations, and we can write the momentum balance equation in this way. We have the x momentum balance written as d rho u by dt plus this is how we have written, but in the course of trying to express this sigma in search of coordinate in search of constitutive relation, we have put sigma ij to be minus p delta ij plus tau ij, and we have now got an expression for tau ij in terms of this like this. So, this is equal to minus p delta ij plus mu times dou u I by dou xj plus dou u j by dou xi plus lambda times dou u k by dou xk times lambda this. Okay, so, this is what we have to substitute for each of the sigma xx and yx and zx, and using this we can write the momentum balance equation, the x momentum, as rho g x, and here we have dou by dou x of this is appearing only in the sigma xx, sigma yx this will be 0 and sigma zx will be 0. So, only dou by dou x of minus p will come here. So, that gives us minus dou p by dou xi, that is this term, and this particular term will come into all these things. Dou by dou x of sigma xx tau xx is written here. Plus dou by dou y of sigma yx is mu dou v by dou x plus dou u by dou y plus dou by dou z of mu times sigma zx will be mu times dou w by dou x plus dou u by dou z. So, this is the x momentum balance equation. We can also, making use of this expression, write down the momentum balance equation in the y direction and z direction. And what we observe from this is that this equation here contains only one new variable p, okay, and of course it has u. Okay. So, mu and lambda are material properties and rho is also a material property. So, in the x momentum equation, if you consider the variables, in the x momentum equation we have u, v, w and p. U is here, v is here, w is here and p is here. Rho and g and all are specified here. In the y momentum equation also we will have the same 4 quantities, z momentum equation also will have the same 4 quantities, and in the continuity equation you will have u, v, w. Okay. So, that means that the total number of variables is just 4 and we have 4 equations: x momentum equation, y momentum equation, z momentum equation and the continuity equation. So, with this modeling, with this constitutive modeling for the stresses that are arising out of fluid motion, we are able to come up with an overall scheme of equations in which there are 4 equations and 4 variables. These together are called Navier-Stokes equations. These are the equations which govern the fluid flow, which determine the fluid flow, but only subject to the condition that rotational strain does not give rise to stress, and that the fluid that we are considering is isotropic, and that the relation between stress and strain rate is linear involving certain constants. So, and that kind of fluid which obeys these conditions of isotropy and linearity between stress and shear rate is called a Newtonian fluid. So, a Newtonian fluid is one which obeys isotropic condition and linearity between stress and strain rate. And which also does not cause any stress under pure rotational strain. So, for a Newtonian fluid, the governing equations are Navier-Stokes equations, and we have seen the example of the x momentum equation. In the next lecture, we will write down the full set of equations which are valid for the Navier-Stokes equations. And common fluids like air and water are Newtonian fluids, but there are many other common fluids like for example, the blood which flows through our bodies, and maybe sugar solution, syrups, which are not Newtonian fluids. So, for such fluids, this relation is no longer valid, and the Navier-Stokes equations are also not valid. You will have to have different kind of constitutive relation which expresses the shear versus strain relation, and there are power law fluids, Bingham plastic models, and then dilettante fluids, and viscoelastic fluids which have even more complicated constitutive relation between the stress and strain rate. Okay. These are all different types of constitutive equations which finally go into determination of the stress which is appearing in the momentum equation as one of the external forces. So, if you have a description of the stress which is arising out of fluid motion in terms of the computed variables, then we can have ultimately a situation where we have equal number of knowns and unknowns, and the problem becomes mathematically a closed problem. Okay. And for that kind of closed problem, for a Newtonian fluid, is the set of Navier-Stokes equations. Okay, so that is what we have for today.